section head loose, the friction factor. When applying pipe flow formulas to practical problems, it is customary to use a control volume analysis. Consider incompressible steady flow between section 1 and section 2 in a pipe flow, for example, in this picture. Point 1 and point 2 as shown in this picture here. Of the inclined constant area part in this picture, the one-dimensional continuity relation is Q1 equals to Q2 equals to constant, and V1 equals to V2 equals to V. Since the pipe is constant area, the steady flow energy equation become from the conservation of the energy equation, we can obtain a relation as a modified Bernoulli equation plus HF. In this equation, since there is no pump or turbine between 1 and 2, for fully developed flow, the velocity profile shape is the same at section 1 and 2. Thus, so we have the velocity V1 equals to V2, alpha 1 equals to alpha 2, reduces the head loss versus pressure drop and elevation change. If we can obtain a relation for head loss, HF equals to Z1 minus Z2, simplification of this relation, plus alpha P1 on rho G minus P2 on rho G, where alpha 1 and alpha 2 is equal. This expression will be eliminated from the equation, and we can calculate on rho G. The pipe head loss equals the change in the sum of pressure and gravity head, that is the change in height of the hydraulic grade line. So the HF is the change in the sum of pressure and gravity, that is the change in height of the hydraulic grade line. Finally, apply the momentum relation to control value. For applied x direction force due to the pressure, gravity, and shear, we can obtain the relation. For force, for example, for the momentum equation, we have this relation. The forces due to pressure, gravity, and shear. Delta Fx equals to delta P due to forces due to pressure from the two sides of the pipe, point 1 and point 2, and the pressure, the force due to the gravity, the volume of fluid, which is rho g p r2l. This is mg multiply the inclination angle and 2 pi rl. 2 pi r l. This relation should be to 0 due to the equilibrium, and we can obtain a relation for delta z, which was the obtained from the energy equation. Head loss can be obtained as this relation to the shear where we have substituted delta z equals to L sinus phi from the geometry of the pipe that was shown in the picture in the previous pages. Note that regardless of whether pipe is horizontal or tilted, the head loss is proportional to the wall shear stress. So the head is proportional to wall shear stress. How should we correlate the head loss for pipe flow problems? The answer was given a century and a half ago by Julius Viscous, a German professor. In 19th century, published the first modern textbooks on hydrodynamics, and previous relations and data such as Hagen values show that for turbulence flow for head loss is approximately proportional to the square of velocity. The proposed correlation is still effective today as this relation. So we can write the head loss equals F L on D V2 on 2G, where Reynolds T duct check. where F is a Darcy friction factor. A French engineer whose pipe flow experiments in 19th century first established the effect of roughness on pipe resistance. The quantity epsilon in this relation is the wall roughness height. Also epsilon the wall roughness which is important in turbulent pipe flow. We added the duct shape effect to remind us that the square and triangular and other non-circular ducts have a somewhat different friction factor than right here than a circular pipe. Actual data and theory for friction factor will be discussed in the sections that follow. By previous equation, we find an alternative for the friction factor, such as we can write F equals to rho V2. For non-circular ducts, we must interpret tau watt to be average value around the duct perimeter. For this region, it is preferred a unified definition of the Darcy factor. Laminar fully developed pipe flow. We are going to discuss the head loss and friction factor in a laminar fully developed pipe flow.